In this lesson 6.2, relate transformation and similarity, you will identify similarity transformations called dilations. So first it's time for the warm-up quiz. So given these triangles are similar and RS over XY, ST over YZ, and RT over XZ would all be at a ratio of 3/2. And given this triangle, EFMN is a ratio of 2:1. If F to G was 4.5, they want you to find NP. So this is 2:1. Half of 4.5 is 2.25. Dilation is a transformation that preserves angle measures and results in an image with lengths proportional to the original or pre-image lengths. The ratio of the lengths of the corresponding sides of the image and the pre-image are called the scale factor of the dilation. A dilation can also be called a similarity transformation. If you remember when we did transformations earlier in the year, dilations did not preserve congruence. They do preserve similarity. So let's look at some examples. So they tell us FEG is similar to FDH, to this larger triangle. Describe the dilation that moves FEG onto FDH. So FH, okay, the original FH is 20. The smaller FG is 10. So the ratio is 2:1. You're talking about moving FEG on to FDH, so you're talking about making everything 2 times larger. If a dilation is followed by any combination of rigid motion, remember the rigid motions will preserve congruence, those can be used to move one figure onto the other, and the 2 figures are similar. So if you see here, ABC is similar to DEF. DEF was congruent to GHJ. It's a reflection over what looks like the y-axis. So ABC is similar to GHJ. So let's describe a combination of transformations. We have A, B, C, and they tell you that it's similar to F, G, E. So the blue is similar to the red. Describe a combination of transformations that moves A, B, C onto F, G, E. So the first thing they did was basically they shrunk this down, and it said a dilation with center B. The reason it's saying center B is the one vertex that stayed in the place, of 2/3 shrinks this or moves this down from ABC to DBE. Then a rotation of DBE with center of E. So they kept E as the center and they rotated this around. The angle of rotation is equal to the measure of angle C. It's the same angle there, and they rotated it. So let's look at some examples. If 2 figures are similar, describe the transformation that moves the blue figure onto the red figure. So this original side here, so we want to move the blue figure, which is 6, onto the red figure. So we're going from a side length of 6 to a side length of 14. That is, reduces to divided by 2, 3/7. Actually, since it's getting bigger, it's going to be 7/3. It's considered a center of B because B is what doesn't change. Okay? On the next one, you can see that this shrinks and is a mirror image. So we're going from blue to red. So from 9 to 6, that's 3 to 2. Since it's getting smaller, it's actually going to be 2/3. Okay? And then it is a reflection at point D. Okay. Dilation, a scale factor of 2/3 with a reflection. Okay, in example 3, we're going to use transformations to explain why ABCD and KLQRP are not similar. We can kind of see that they don't look similar, but let's look here at what happens to each side. 12 to 8. That ratio, dividing both top and bottom by 4, is 3 to 2. Okay? This side here, 9 to 6, is 3 to 2. This side here, 6 to 4, is 3 to 2. 9 to 6 is 3 to 2, and 12 to 8 is 3 to 2. But if you look at these, even though these are congruent, and you would need to actually shrink this down and flip it to see if it works, but it does not look like P and E are congruent. To actually do this problem, you would actually have to use some kind of software to shrink this down and also flip it to see if they line up on each other. So in this next picture, they actually show that what they did was they shrunk this down so that the sides matched, but when they reflected it over the axis, you could see that these were not congruent. Those angles were not congruent, therefore the shapes are not similar. And in example 4, a graphic design, a design for a party mask is made using all equilateral triangles and a scale factor of 1, 2. Describe transformations that move triangle A onto triangle B. And describe why triangles C and D are similar by using the given information. Okay? So the first thing here, let's look at these, is for A. The scale factor is a dilation with a scale factor of 1/2, followed by a clockwise rotation of 60 degrees. So we dropped it in half, okay, and then we rotated it 60 degrees. Triangle C and D are similar because all pairs of corresponding sides are proportional. So let's look at it again now. C and D. Okay, so this is 1/2 of this, and they're all equilateral triangles, which means if this is half of this, then these are all going to be marked like that. So they're all going to be congruent. They're all going to be same side. All the sides are congruent. Refer to the floor tile design shown below. In each design, the red shape is a regular hexagon. So if this is a regular hexagon, that means all of the sides on the red are equal, are congruent, and all of the angles are congruent. Okay? Here in tile design 1, we have tile design 2 and tile design 3. We're going to click back and forth to look at the questions here. So in tile design 1 is made using 2 hexagons. Explain why the red and blue hexagons are not similar. In order for them to be similar, all of the sides have to have corresponding ratios. And in tile design 1, all of the red sides are the same size. In the blue hexagon, 3 of them are congruent, they appear to be shorter, and 3 of them are congruent to each other and appear to be longer, but not all 6 are congruent to each other, therefore they're not going to be similar. Okay? Tile design 2 is made up using 2 similar geometric shapes. Describe the transformation that moves the blue hexagon to the red hexagon. I'm going to figure that out. I'm going to draw lines from each of the vertices to the opposite vertice to find the center of this blue hexagon. Then I'm going to do the same thing on this red hexagon, although I want to use yellow so you can see that a little bit differently. I'm going to show you how we can use a protractor. Okay? And I want to line this protractor up so that it meets at the center of these 2 hexagons. When trying to get to rotate this, come on, where's the rotate? There we go. That didn't work. When I rotate this, I want to get it so that this black line is on one of these orange lines. It's going to be easiest for me. And you can see that to move this blue point to this yellow point, or this yellow point to this blue point, it's going to be 30 degrees. The difference from yellow to blue, red to orange, is 30 degrees. So it is going to be a 30-degree rotation. Okay, I'm going to go ahead and close that now so I can look at the last problem. So when they said describe the transformation, that's going to be a 30-degree rotation. I think I said earlier dilation. We're going to actually end up using a rotation. Tile design 3 shows congruent angles and sides. Explain why they are similar using the given information. See that all of these sides are congruent. That means it's regular. And if they're all regular, and then there's a formula that I can figure out the measure of each of these angles. So the sides, the angle measure, of a regular hexagon is going to be the same in any regular hexagon. Since they're both regular, they must both be similar. And if the lengths of all sides of one polygon are proportional to the lengths of all the corresponding sides of the other polygon, then they must be similar, because the ratio of the angles are not always going to be the same. You can have the same sides, but skew them at different angles so that they're not always similar. You have to know that one of the angles, or all of the angles really, are similar. So now it's time for the daily homework quiz. Describe the dilation that moves the smaller figure onto the larger figure. So as you can see, it's increasing twice, okay? Okay, daily homework, Chris. You can see that the original is 8, and so this whole height, if this is 16, 8 plus 16 is 24, so you can see that it's getting 3 times larger. Okay, describe the dilation that moves the smaller figure onto the larger figure. So this was originally 5. 5 plus 3 is 8. So the original figure is 8/5 larger. Once again, the center of dilation is at the center of the circles. I'm going to, in GeoGebra, put this triangle in. So it's 1, 1, negative 2, 2. And point C is 2, 2. Now, I'm just lucky that these are A, B, and C, and then D, E, and F. So GeoGebra is labeling like them like that. Otherwise, I'd have to go into GeoGebra and change the names. And I know you can't see E. I'll move that in a minute so you can. Oops, 4, negative 4 is point E. So let me come over here. Let me move the graphics view a little bit so you can see that. Now I want to connect these. So A, B, C, back to that. And I want to connect D, E, F, back to that. So now, okay, I don't really want point G, but I'll just ignore it for a minute. I want to reflect an object about a line. So I want to take this shape and I want to reflect it about that line. And I was just able to do that. So now I can see it lines up a little bit better. Now this is larger than this. And it looks to me like if I look at segment A prime, D prime, it looks to me that's about half the distance of D prime F. Okay? Or actually it was D F. Sorry, this is C prime. You can't see those there. So what I want to do is I want to actually dilate. Okay? So I want to dilate this. Let's start there. By about a factor of 2. Okay? So now it's here. It's twice as large. And now what I actually want, it looks like this is going to slide right onto that. But I want to see, I want to make sure it really is. So I always have a little bit of troubles with this. But I want to translate object by vector. Don't worry about what vector is or how it works. I just know that it's going to work. So if I click on this point, I didn't get my vector line. So if I click on this point again, I want to move that point down to here. And at the same time I do that, it didn't stick. So let me do that again. I want to translate this point, try this again, this point down to here. Try this again, this point down to there. So now, I think, if I do this right, nope, did not do this right, that I can then click on this object and try and move it, and it's not moving. But I can see that if I go from -6, -2, and I move everything over 1 and down 2, it's going to line up. And I can see that if I take this point and I move it, this was down 2 and over 2. If I move this down 2 and over 2, and if I move this down 2 and over 2, it's going to move. The point of this whole exercise is not to actually map it out per se, but it's just to start to get an idea of what I would need to do to this figure to make it lay over this figure. So let's look at what they have. They're sample answers because I could do a number of things. If you remember, let's go back and look at the figure. I reflected it first, then I dilated it, then I translated it. Their sample answer was they dilated, then they reflected in the x-axis. So they made it larger and then they reflected. They didn't need that translation. As long as I can describe transformations to show that the figures can be moved onto each other, I can prove that the figures are similar. And so you can look through it. These are the problems from section 6.2 that your homework will come from. Okay? I know there's a lot of new material. I will admit this was a much more technologically difficult presentation to make. I certainly hope it helps you.